I think I can start. So thank you for coming to my presentation. I'm very honored to be here because my first ever Scala Global Tech Conference was Scala Days 2019, 6 years ago, and I came back here this time as a speaker. So my name is Rikito Taniguchi. I'm a software engineer at VirtusLab, and I've been working on Scala compiler tooling like Metals for several years, and a little bit on Scala native. And recently, I'm working on Scala.js for WebAssembly compilation, collaborating with Sebastian. So as the title says, bringing Scala server-side Wasm with WASI and component model. I'm going to talk about the WebAssembly support in Scala, but it's more specifically on server-side Wasm usage. So some of you may know, as of version 1.17, Scala.js started supporting experimental WebAssembly backend. Did you know that? Okay, because Sebastian talked about it. So maybe you know at least some of what is the WebAssembly. But so you can generate the WebAssembly binary instead of JavaScript, and the generated Wasm binary can run on major JS runtime like Chrome and Firefox and Node.js and Dino. And by compiling to WebAssembly, we can run the program faster than JavaScript in some cases. And we can implement some new features based on WebAssembly, which we couldn't implement on JS only. So this is great. And now some of you may think WebAssembly is so optimizing the browser applications because WebAssembly says WebAssembly. It's yes and no because, yeah, it's for optimizing the browser application, but there's not the full story. WebAssembly is more than browsers. For example, now US government is now pushing the WebAssembly for cloud-native security, and Microsoft is releasing the WebAssembly-based tools for AI agents, and creator of Docker mentioned that he wouldn't create Docker if Wasm and WASI existed back in 2008. So people are really excited about WebAssembly as well on outside of browsers. And I'm also excited about server-side Wasm, and I'm started to working on server-side Wasm support in Scala in the fork repository of Scala.js, Scala Wasm. And the current Scala.js generates the current Scala.js Wasm backend generates the Wasm binary and a tiny little bit of JS helper functions. So it works only in JS environments, and we cannot use it in standalone Wasm runtime such as WasmTime and WasmEdge. But our work in progress compiler generates Wasm binary independent of JavaScript, and it runs on the standalone Wasm runtime, so it's WasmEdge and WasmTime. And cool. So, but why? Why people are so excited, and what is the benefit of compiling Scala to server-side WebAssembly? So in this talk, I'll talk about what is the selling point of server-side Wasm and what exactly is the WebAssembly. And here's the list of items I'm going to cover in this talk. I'm going to start with the challenges in cloud computing, which is WebAssembly going to solve. One of the example WebAssembly can solve. And then I'm going to talk about what is WebAssembly and how it's going to solve the challenge in cloud computing. And then finally, I'm going to explain the current state of server-side Wasm support in Scala. So this is more like and yeah, this talk is not designed for talking about Wasm on browser thing and details on Wasm spec and compiler implementation, which is covered by Sebastian talk. So and this talk is more like a high level, what is the motivation of server-side Wasm thing, and a little bit of current state of server-side Wasm in Scala. And disclaimer again, the server-side Wasm support in Scala is not still work in progress. There is a lot of demos, but this is not yet you can enjoy in production from tomorrow. But we are working on that. So, all right, so we're going to start with a quick little summary of what cloud computing is. It's not that simple, but we can say, simply put, we can say cloud computing is running your program on someone else's computer. Here, someone means AWS or GCP things cloud providers, and we upload our applications to those cloud providers, and we run our application on their big, large computer, sharing the computation resources with other people. And when we run program on someone else's computer and sharing the resources with other people, the important challenge is safe and efficient runtime isolation, because you don't want other people's program running on same computer to read or write your program data or memory, and of course other program running back in the program on the same computer shouldn't crash the whole computer, and your program shouldn't break. So all the programs should be isolated. So the Linux container is the most famous. Linux container using something like a Docker would be the most popular option for isolating today. And each container image packages from OS user run and language runtimes and your applications. And and we share the host kernel, but each container is isolated, and each of the application cannot access to the other container inside the other container. So the benefit of the Linux container-based isolation is the flexibility of installing any OS user run or packages and runtimes, runtime dependency, anything. But those flexible layers can be attack surfaces for attackers, and it can be a and another challenge is size and startup time, because container image install a lot of things, and it tends to very large, and loading the large container takes a lot of time. So, and on top of that, for example, if we are running the JVM application, we have to wait for JVM to start up when we cold start the container. So the workaround for the container vulnerability and cold start problem would be using a small container image, for example, Google's distillers image. So if we don't have any software in the container, it's less dependency, which means less software, which means more secure, and it starts faster because it's smaller. The another workaround is to keep running the container instances while it takes some extra money to keep running idle application. Warming up the container eliminates the cold start problem. So this is a workaround. But what if you are running the really, really high traffic application with unpredictable traffic spikes, maybe Twitter or X, or maybe some 2C applications? It's sometimes there's unpredictable traffic spikes, and in that case, maybe keep warming up instances can be prohibitively expensive, and smaller container still takes some time to start up. So maybe it's not enough. And what if you are deploying your part of your application to resource-constrained environments like CDN Edge or IoT devices? Its container is too big. But what we can do, we already slimmed down our container image to the limit using distillers container. But what if we could eliminate all the Linux layer altogether? Because this is the whole reason we are the challenge in cloud computing. And this is where WebAssembly comes in. And while container-based isolation packages a lot of things from container runtime, OS user run to language runtime, and it gets broadened. But WebAssembly runtimes takes responsibility to isolate each application, and it provides a lightweight isolation without Linux container. I'm gonna talk about it later. And so WebAssembly can start up really fast because there's nothing other than your web application binary. And it's more secure because there's no software running inside the Wasm process. So is this really fast? So let's check it. We're gonna try comparing the startup time and size of JVM application package into Alpine container and native Scala native application package to distors and compare it to WebAssembly. So the first thing, all the application gonna be a hello world application, and we gonna compile to JVM native Wasm. The first thing is this one. Yeah, this is just a hello world application, and we are going to compile to JVM application, JVM, and link it using JRlink SPT native packager and copy the thing into our Alpine image and run it. So that's it, and I'm gonna Docker run, Docker build. Scala, yeah, this one. And yeah, because I already built it. And let's see how big it is. Docker inspect scene Scala and JQ to check the size. Yeah, this is the size. It says 37 megabytes. It's not bad considering the JVM is very big. So let's take a note here. 37 megabytes, and let's check how long it takes to run hello world application. Since Scala. All right, it's something like 350 milliseconds. So it's also not bad to concept. It's a core thought, but the important number is this thing. It's oh, did you see it? Can you see it? It's only a 5% or 7% of CPU time is used. So which means like a 95 or 96% of the time is spent on waiting for something. Maybe one is printing the hello world to the std out, but I think most of the time is spent for waiting for the container and JVM to start up. Okay, so now next thing is native. This is also this is just a hello world, but this time we are going to use a Scala native, and we link the Scala hello world to native binary using Scala native and copy the resulting binary into distors image. It's going to be really small, I think. And Docker build. It's also fast because I already built. And let's check Docker inspect Scala native JQ size. And yes, this is the size, and it's written in bytes, so it is 1.4 megabytes. It's really much smaller than JVM. Nice. Because it's a native binary and it's a distors. And so let's check how long it takes to run the application. It is around 200 milliseconds. It's much faster than JVM, and the CPU time is around 13%. So yeah, it's better, but we are still waiting for using a lot of time to waiting for something, maybe a container to start up. Okay, so the final thing is checking the WebAssembly. This is by the way, this is our forked repository, and let's see, hello world WASI, and this is a little bit different from the previous example, but basically this I don't explain the details, but this WASI CLI run thing means this is the endpoint of this application. So in this function, we just do a print hello world, and that's it. So this is basically just a hello world application. And let's build it. Oh, and make, yeah, this is, I don't remember what is, yeah, make component. Yeah, this is, I don't also explain the details, but WASM2's component thing is just transforming the our generated WASM binary to be able to run on WASM time or WASM edge things. And WASM OPT is the optimizer for WebAssembly, and we are just optimizing the WebAssembly binary. And this main WASM is going to be a final binary we're going to run. And let's check how big it is. It is 26 kilobytes, so it is much, much smaller compared to other things. And let's check, see how long it takes. Oh, by the way, maybe you think this is unfair comparison because the first two examples are run in Docker, but the last one gonna be is just a WASM binary, and it is not going to run through Docker. But believe me, trust me, the low-level container runtime for WebAssembly gonna just do running the WASM binary using WASM time. That's it. So this is basically what low-level container runtime gonna do. So this is kinda fair comparison. So let's check it. All right. And oh, what's going on? But anyway, it seems like first run is a little bit slower, but it's basically even the first one is only 48 milliseconds. It's 4 times faster than native, and the CPU time is 41% or maybe 88%. So most of the time is spent for CPU time and not waiting for WASM application to start up. So this is awesome. So right? All right. So actually, there is some. Oh, sorry. All right. So actually, this is summary. So because I experimented beforehand, and the JVM was 35 megabytes and native was 1.5 megabytes, but WASM and WASI was going to be much smaller, 26 kilobytes, and it takes a much smaller time. Like JVM was 300 and native was 250 or something, and WASM and WASI was 25 or something milliseconds. So it's much, much faster, and it is already isolated. So hi, yeah.
I'm just wondering, have you tried to run the Java native one natively and see it?
Java native?
Yes, the Java native version there. Have you tried to run it without the Docker around it, just to get the numbers running it?
So you mean Java
No,
without Docker
Scala
container?
Native. Yeah, Scala native, run it without Docker.
I haven't tried,
Okay.
but I can try maybe, but later.
All right.
Yeah, sure, but it's going to be faster, but yeah.
Just to confirm, Scala native is not like GraalVM or anything, right?
Yeah, it's not a Scala native that compile to LLVM IR, not a GraalVM.
Okay.
Yeah, thank you for confirming. All right, if there's no any question, I'm gonna keep talking. So, all right, finally, I'm gonna time to talking about WebAssembly, is what the WebAssembly is. So WebAssembly is just a binary instruction format where you can run in JS runtimes such as Chrome, Firefox, and Node.js, or you can run in a standalone WASM runtime like WASM time and WASM edge. And it has quite a lot of characteristics, but the most important thing for server-side WASM is fast and safe and polyglot and portable. So first of all, WASM is language independent and platform and hardware independent. WASM is very, very simple language by design, and it is not connected to a specific programming language paradigm like object-oriented programming thing. So this generic language design allows a wide range of programming language from C or C++ and Rust to or Kotlin, Scala, Go to be compiled to WebAssembly. And this is really interesting design difference compared to JVM, I think, because JVM is Java bytecode is really specific to Java, so Java program can be compiled to really efficient Java program, but when it comes to compiling from different language, non-Java-ish language like C or C++ to JVM, it's gonna be challenging. So this is a difference between Wasm and Java. But on the other hand, Wasm is same as Java. Wasm is portable as same as Java. So it is platform independent and OS independent. So you write once and run anywhere applies to WebAssembly as well on top of the JVM. And most importantly, WebAssembly provides a safe environment to run untrusted code. Here, untrusted code means, for example, a program uploaded by user. This is important because from cloud provider's perspective, our application program is untrusted code. And maybe your third-party library is also untrusted code if you are not examining all the things line by line, or maybe these days AI-generated code is also untrusted code, maybe, if you don't believe AI. And Wasm follows the least privilege principle of least privilege. So by default, Wasm cannot have any side effects on the outside world. For example, what Wasm cannot do is, one is it cannot access variables or memory outside of its own, and it actually cannot do anything by its own, like it cannot print anything to std out, and it cannot read or write files, and of course Wasm cannot send a HTTP request by Wasm by themselves. So what WebAssembly can do? It is two things. One is do some computation and call the imported function. WebAssembly has an interesting feature that importing the functionality from host environment. For example, this right-hand side is a WebAssembly program text format, and it imports the logger function that takes a 32-bit integer. And the left-hand side is a host environment, in this case, JavaScript, and it provides a logger function implementation using a console log. So this is how WebAssembly prints something to the std out. So WebAssembly needs to going through the host environment in order to access every host system resource environments, including std out. And WASI, WebAssembly System Interface, provides a standardized interface for system operations like print something or sending HTTP requests or reading file system, and so on. And it defines a collection of standardized WASM interface, WASM import signatures for something like clocks or writing something to std out or HTTP requests or file system and sockets and so on. And those implementation should be provided to Wasm VMs, usually. There's an exception case, but anyway. By using WASI, we have a standardized interface, so it's gonna be, Wasm program gonna be portable. And by standardizing the interface, Wasm VMs can be now implements a capability-based access control. For example, imagine a program that reads and print a file content, but this program fails to read a file by default because Wasm VM denies to read a file system by default. So in order to Wasm Edge to allow to access host file system, you have to pass the --d option. This is something like a Docker to access a host file system thing. So yeah, Wasm by default deny everything like reading the file system and sending HTTP request. So in summary, WASM can be compiled from a wide range of programming languages, and it is portable, and it provides a lightweight resource isolation. So thanks to these characteristics, WebAssembly is used as a lightweight alternative to Linux containers with ultra-fast startup time and less attack surfaces. And this is why server-side WASM is important. It is mostly about lightweight isolation. So this is the most important thing I'm gonna tell you in this talk. Oh, okay, so what time, how long I gonna left? 14 minutes, okay. I was planning to demo, but actually I'm running a demo about deploying the Scala Wasm binary to Kubernetes cluster, but I'm running out of time. It's only 15 minutes, and I have another cute little demo, so I'm gonna prioritize it, and I'm gonna skip this. But I have a good description of the demo, and I can show the demo later in the lunchtime, so please let me know if you're interested in, and I'm gonna share this link in Internet X or LinkedIn somewhere later. So I'm gonna skip it, sorry. So all right, I've been talking about WASM and WASI, and now let's finally talk about server-side WASM in Scala. So we saw WASI is a standardized system interface for WASM, but remember, and WASI is just a definition of import interface, something like this. So how can Scala programs call WASI interfaces? How to Scala program to call these imported functions? To talk more details about WASI, we have to talk about another concept, WASM component model. WASM component model is a specification for safe and easy cross-language function calls in WebAssembly. It is composed with mainly two or three things. One is WIT. WIT is WebAssembly interface type. WIT is interface description language that has a high-level data types like a string, list, variants, optional, and result types, and so on. So we can describe the interface from WebAssembly using this WIT interface. So you can think about this as kind of protocol buffer thing. And the canonical ABI is because WebAssembly doesn't have any these high-level data types like a string or list or variants. WebAssembly doesn't have any of this. There's only a ith32 or number things and reference type. So canonical ABI defines how those high-level data types can be mapped to the low-level core WebAssembly. So for example, a string can be needs to be layout on linear memory and we represent string using a memory offset and its length, so something like that. That's canonical ABIs, by the way. The end user shouldn't care about it because it's really complicated. So to call the WASM component defined interface from Scala, we use a binding generator called WIT-bindgen, which I haven't supported for Scala yet, so I'm currently writing the binding code by hand. But anyway, WIT-bindgen generates the glue code for the given WIT interface, and we call the component function using the generated code. And actually, this generated code going to be compiled to some function called procedure following the canonical ABI, which is end user shouldn't care about it. So basically, WIT-bindgen generates the glue code. For example, this greet function in WIT going to be compiled to Rust like this. It takes a immutable string and returns a string. And in our current Scala compiler, it receives a string and it returns a string. So we can call the WASM component function based on this generated function glue code. So another demo. so because I want to show it, so that's why I skipped the another demo. And where see my cursor? Sorry. Wait a sec. Oops. Ah, yeah, here it is. Sorry. So what I'm gonna show you is calling the Rust-defined function from Scala, because Wasm component model allows it. So hello world. Yeah, this one. Clear. And I don't need this anymore. So what we gonna implement is this is with interface we gonna implement. We have, this one, greet function is defined, and there is two word. A word is some kind of compilation unit in the Wasm component model world. So we have two compilation unit. One is a Rust and one is Scala. And Rust gonna be exposed a greeter, which means Rust gonna implement this greet function interface. And Scala has an import greeter, which means Scala gonna import the implementation of greet function from outside world, and this time Rust. So the first I'm gonna show the Rust implementation. So this is the implementation of Rust. You don't worry about even if you don't know about the Rust, it's really simple. So this is a greet implementation. It receives a string, and it returns string. And what they're gonna do is just receive the string and say hello by using a Ferris say, which is a really cute Rust character. Ferris gonna say something, and returns the resulting string back to Scala. So that's it. And let's see Scala side. So on Scala side, so I don't explain details because this API is not really fixed. But anyway, this component import Scala Wasm hello world greeter greet mentions that this function is import interface for the greet function defined in the with interface. And this is the main function, and we're gonna greet Scala. Oh, let's do maybe Scala days 2025 or something, and we're gonna greet to Scala days 2025 and prints the resulting string. So that's it. So it should be Scala program start from here and call the Rust function and Rust gonna return the string and print from Scala, and that's it. So let's build it. Finished, and make this is something I'm gonna transpile the generated Wasm module binary to some form of linkable format. So this is, you don't have to care. And I gonna make compose or something. Yeah, this is WAC plug is some kind of linker. So what we are doing here is linking this Rust generated Wasm module, Wasm component binary and Scala generated main Wasm component binary together. And so this is kind of static linking and generates out Wasm as a resulting binary. So let's run it. Hopefully it works. Yay. So Ferris is saying hello to Scala days. Cute. So yeah, so this time we call a Rust function from Scala, but we should be able to define a WASM component function in Scala, and Rust can call it, and vice versa. And other languages that implements WASM component model should be interoperable each other. So let's get back to the presentation. I have only a few slides left. So yeah, what I was talking about, yeah, I was getting back to WASI. Remember, WASI is a standard system interface for WASM, and the current version of WASI, WASI Preview 2, is defined based on WASM component model. That's why I was talking about WASM component model. Long story. For example, the getStdout function is defined like this in WIT. So it just returns the output stream, and output stream has a method, something like a write, that takes a list of bytes and writes something and returns a result type. So this can be also, with binding, can be generates a glue code for this WASI definition, like getStdout function and write function in Scala. Yeah. So yeah, WASI is based on WASM component model. So if once we implement the WASM component model, WASI support is available automatically. All right, now I talked about the benefit of server-side WASM, and I showed some demos. But now what is, I said the WASM server-side WASM compiler is still work in progress, so what is missing? One is the WASM component model support, because my current API design of WASM component model is, I'm not very proud of it, so I need to polish it and finish it up, and also I need to implement the with binding based on the API. And another challenge is that in order to generate server-side WASM, we cannot use JS, because WASM time and WASM edge doesn't have any JS environment. But current Scala.js has a lot of JS interpolation in JDK implementation, so we have to re-implement some part of JS interpolation part of JDK into pure Scala or based on WASI. So this is something we are working on, and actually we are working on it, and there is around 6,000 tests should be passed in server-side WASM environment, and we are currently 4,300 of tests is green. So yeah, I'm gonna keep working on it. And finally, I have to talk the elephant in the room. And now, because JS interpolation, I mentioned that JS interpolation is not available in server-side environment, but it is also the same to the third-party libraries. So I think the CATS effect or FS2 things like system libraries should be using a JS interpolation a lot, but it is not reusable in server-side WASM environment, unfortunately. So we have to re-implement those JS interpolation based on WASI things. So that's going to be a biggest challenge for ecosystem. But this rewrite should be needed only for the foundational library like CATS effect or FS2, and other libraries that doesn't use JS interpolation shouldn't be a problem, and so hopefully not many libraries needs to rewrite. All right, so this is the end of the presentation. What I want to tell you in this presentation is server-side WASM is about lightweight isolation, and WASM component model is secure language interpolation, and you can call the Rust function from WASM component model. And we are working on it in Scala Wasm, Scala Wasm. So thank you for listening, and thank you for your attention. Yes, his.
I mean, the time is technically over, but you're free to discuss for as long as you like.
Yeah, sorry.
So I have a question for specifically for Scala Wasm. So Scala JVM and Scala.js has some difference in semantics, right? Like, integers work a little bit different, things like that. So are there something the same for backend WASM as well?
Currently, as far as I know, there is nothing. I mean, it's basically the same as Scala.js because we try to mimic the semantics of Scala.js. So yeah, right? Okay.
That worked. Wow. Thank you for the talk. At the moment in the Scala native, we have a very comprehensive sort of I/O-related amount of JavaLib stuff implemented, like file systems and all of that. How do we not lose our minds and re-implement yet another JavaLib now in WASI?
Yes.
Because we can also could we make it work on Node.js with just like running await directly on the Node.js APIs without the async stuff? So what I really want to get to is that we have a single JavaLib implementation that can be used on Scala.js, on Node.js, and in Scala native without having to maintain 2 different or 3 different artifacts.
Yeah. That's really something I really want, actually.
More context.
So Scala.js and Scala native typically, historically have had their own JavaLib each. Scala native, JavaLib covers a lot more than Scala.js, actually. They do the I/O stuff. In Scala.js, since the core says ECMAScript as a spec doesn't give us I/O, so you won't get it either. And then you can build third-party libraries that do it, like FS2 or Cats Effect or the other ones. For WASM, the story is actually closer to the JS story in the sense that WASM per se doesn't have I/O. Again, you only get I/O because you import some specific WASI things. So we would also leave all the I/O stuff to separate libraries, right? Not put them in the core. And the JavaLib between WASM and JS is going to be shared. So we only have very specific places that Rikito identified to have, if it's for WASM, do this, if it's for JS, do this, but otherwise, like, the 50,000 lines of code are shared in that space.
But the I/O part can be shared between the native and the WASI part. Can we have another artifact that implements JavaLib I/O parts with WASI components?
So, yeah, but we'll leave it to third-party libraries to figure out what their build should look like. They can also do if it's JS, do this, if it's WASM, do this. For native, it needs to be a different source file. Yeah.
Thank you.
Thanks for the talk.
Yeah.
Now, I know WASM itself is still like a single-threaded environment, but then if this is supposed to be an alternative to Docker, then people might expect the multi-threaded. So is there some proposal for a which version of threading, or is there like a way to communicate between 2 separate WASM processes or something?
Sorry, so you were asking about threads implementation in WASM. It's a little bit complicated story. There is a WASI threads proposal, version 1-ish thing. It's already, I remember it's a stage 4 or 5, which is really mature, but it is really designed for C or C++ thing. But when it comes to, because Scala to WebAssembly compiler uses something called WASM-ZC, and WASM-ZC, for WASM-ZC, those threads proposal is not designed for WASM-ZC, so they are trying to re-implement the WASM threads proposal from level 1, so stage 1. So there is a threads proposal, and maybe in future we could implement WASI or threads in Scala.js, but it's going to be a long story.
Thank you.